Welcome to lesson number 22 in our series of building stock prediction dashboard with Python and Streamlit. We still are in the phase of trading predict, and our last session we built the create RNN model method. Today we are going to work on create LSTM model, which is pretty similar to RNN. And the next session will be designated for preparing the sequence data for those models. And after that, as you can see in our earlier code, we have training purposes for each of models. So we are going to work on train for both RNN and LSTM models. RNN model and LSTM. So this is our short time planning that we are going to work on. Now let's get to the code for LSTM model. First, couple of words of discussion. Why this exists? Because this method will define the architectural and training configuration of LSTM-based neural network. It is designated for time series regression, which typically is used for future prices and returns because financial data is sequential. Relationships are temporal, so with whatever happened previously does matter. And comparing with the simple regression, long-term dependencies here are captured. The most interesting thing though is that in my daily prediction dashboard, which you can see now, we can see that MAPE, which stands for mean absolute percentage error by model, we have lower values for ARIMA, linear regression, and random forest comparing with RNN and LSTM, which means that there is always a room for improvement of your models with configuring the layers and the depth of model work. So let's proceed. We have defined a model signature, method signature, which here includes the input shape, timestamps, time steps, and features, and it is explicitly passing the input shape. This ensures that model will be reusable for different symbols, and it will shape consistency across the training and interference. So remember what I just told you, we are going to use this in training of LSTM. Now let's have the code, shall we? One liner here goes for create LSTM model with initial architecture. Okay, this autocorrection is still killing me, but we will reuse whatever is possible. So model will be sequential, and let me actually update it with the correct one. LSTM with 120 return sequence true, input shape, input shape. Then let me have the code written, and we will go line by line why is something written as it is written. Drop out the 3, then goes the next LSTM64 return sequence, not false but true. Then again we'll go batch normalization and the drop out, and after this we will have LSTM 32, turn sequence now will be false. We will have batch normalization and drop out. And the dense activation rule, but here we'll go 16 and linear. So here we will be closing our data script. Okay, now let's go line by line. We are selecting a sequential model here with multiple layers. Why sequential? Because it's appropriate for data flow linearly through layers. As you can see, we have 3 layers of the LSTM. First layer, 128, return sequence true, and input shape, input shape. 128 unit. Batch is large enough to capture complex temporal patterns, and typically the first layer uses the highest capacity. We have return sequence equal true next, because this is required because we have another methods following. As you can see, this one has also true, because after that comes LSTM32. And here, as we don't have anything coming after it, it stands for false. And with this, we are giving the output the full sequence, not just the final timestamp. And input shape, we define expected structure of time series input. We do then batch normalization. Why do we do it and what it does? It does stabilizing, it brings stability for training by normalizing activations. It helps with faster convergence, reduced sensitivity to learning rate. In time series network, this is especially useful due to the non-stationary data. You can see that we are using this in all 3 layers. Then comes the dropout of 30%, 0.3. Why? Because financial data is noisy, because this prevents memorization of specific historical patterns, and this helps to force the model to generalize instead of overfitting. Again, you can see that this parameter exists for all 3 layers. We go then by reducing the size, progressive compression. Early layer here will detect the broad patterns. Later layer will refine the higher level temporal signal. Same goes for this one. We still have return sequence equals true, because as I mentioned, we have another layer following. The third layer, now we have it equal to false. This is final temporal aggregation, converts a sequence to a single context vector. Then again we use the normalization and the dropout. Dense layers, what they do? Dense 16, this acts as a feature transformer, introduces non-linearity and allows interaction between expected temporal features. Then comes the linear part, outputs a single continuous value. Linear activation is correct for price, returns, normalized values. We covered the model activation. Now let's compile it. Model, compile. Optimizer, Atom. Okay. We will again go with modifying this according to our needs. the learning grade 001 and click norm 10. Let's dive into this one. Optimizer Atom with adaptive learning rate per parameter works well on noisy, non-stationary financial data. Learning rate. It is a conservative default value and stable for deep LSTMs. Why deep? Because we have 3 layers in it. Clip norm 10, which prevents the exploding gradients, and this one is crucial for RNN and LSTM stability. The loss, which is mean squared error, it used to penalize large errors heavily, encourage accurate point prediction, and standard for regression tests. And the metrics here goes MAE, which is more interpretable than mean squared error. And reminder, MAE stands for mean absolute error. It directly reflects the average prediction error. And in return, for this function, we are returning a model. Model is returned untrained. It allows the separation of architectural definition, training logic, and hyperparameter tuning. I hope this was helpful. Again, if you are looking for deeper dive, you can check it in Medium.com. Here I am. And scrolling within this, you can find the appropriate definition for the LSTM too. Let me just find it. It was a while ago when I did this single presentations. It was April 2024, I believe. Somewhere at that time. Yes, here it is. No, it was May. So with this article, if you are a member in Medium, you can check the explanation of LSTM deeper and explanation of the code doing this for single model and returning the results. Stay tuned, and as we can see here, our next session will be designed for prepare sequence data method. Thank you for your time, and see you at the next session.